Slide 1, Acute Stress and Catecholamines. Hello everyone, welcome to Lecture 3. Today we'll be diving into the fascinating world of acute stress and catecholamines, specifically adrenaline and noradrenaline. We'll explore the fight or flight response and the crucial role these hormones play in it. I am MS Nadeem, PhD. The adrenal medulla, the inner part of the adrenal gland, is composed of chromaffin cells. These cells are specialized to produce and secrete catecholamines. Interestingly, there are two main types: adrenaline-secreting cells, making up about 90%, and noradrenaline-secreting cells, which account for the remaining 10%. The hormones secreted by the adrenal medulla are known as catecholamines, named for their derivation from catechol. The primary catecholamines are adrenaline, also known as epinephrine, and noradrenaline, or norepinephrine. Notably, adrenaline makes up about 80% of the catecholamines released. Let's look at the typical levels of these hormones in the bloodstream. Adrenaline usually sits between 30–60 pg/ml, but during stress, it can surge to 300–600 pg/ml. Noradrenaline's resting level is 150–300 pg/ml, and it can jump to 500–1000 pg/ml under stress. Both have short half-lives, around 2–3 minutes, allowing for rapid responses. Catecholamine synthesis is a multi-step process. It starts with phenylalanine converting to tyrosine. Tyrosine is then transported into the chromaffin cells of the adrenal medulla. Inside these cells, tyrosine is converted into dopa, which is then decarboxylated into dopamine. This slide visually summarizes the synthesis pathway we just discussed. You can see how tyrosine is converted into dihydroxyphenylalanine, then dopamine, norepinephrine, and finally epinephrine. This cascade of enzymatic reactions is essential for producing these vital stress hormones. Slide 7. Catecholamines are metabolized through methoxylation and oxidation. Adrenaline is methoxylated into meta-adrenaline and noradrenaline into metanoradrenaline, both by catechol O-methyltransferase, COMT. These metanephrines are then oxidized into vanillyl mandelic acid, VMA, by monoamine oxidase, MAO. The body eliminates catecholamines through urine in three main forms. About 15% are excreted as free adrenaline and noradrenaline. Around 50% are excreted as free or conjugated metaadrenaline and metanoradrenaline. The remaining 35% is excreted as vanillyl mandelic acid, or VMA. Slide 10. Catecholamines exert their effects by binding to adrenergic receptors, which are divided into alpha, and beta types. This slide focuses on the alpha adrenergic receptors. This slide details the beta adrenergic receptors. Adrenaline significantly impacts metabolism. It boosts oxygen consumption and carbon dioxide removal, increasing the basal metabolic rate, hence its classification as a calorigenic hormone. Furthermore, adrenaline elevates blood glucose levels by stimulating glucose production in the liver and muscle. This slide illustrates how adrenaline increases blood glucose levels through glycogenolysis. Glycogenolysis is the breakdown of glycogen, the stored form of glucose, into glucose molecules. This process is crucial for providing a rapid energy source during stress. The key enzyme in glycogenolysis is glycogen phosphorylase, GP. Its role is to break down glycogen into glucose. When energy is needed, glycogen phosphorylase is activated through phosphorylation, leading to a surge of glucose release. Adrenaline has a profound effect on heart activity, more so than noradrenaline. It increases heart rate, chronotropic effect, the force of contraction, inotropic effect, and the excitability of heart muscle, bathmotropic effect. It also improves contractility, dromotropic effect, and increases blood supply to the heart, by dilating heart arteries. Noradrenaline primarily affects blood vessels, causing vasoconstriction throughout the body, earning it the title of a general vasoconstrictor. Adrenaline also constricts blood vessels in skeletal muscle. Consequently, both hormones contribute to an increase in blood pressure. Catecholamines require the presence of glucocorticoids, steroid hormones from the adrenal cortex, to exert their vascular effects. Adrenaline increases systolic blood pressure by enhancing the heart's contraction force and cardiac output. It also decreases diastolic blood pressure by reducing total peripheral resistance, an effect opposite to that of noradrenaline. Slide 19. Overall, the hypersecretion of catecholamines leads to hypertension. This slide explains the complex signaling pathways involved in cardiac hypertrophy induced by adrenaline and noradrenaline. It involves a cascade of events, including CAMP production, protein kinase activation, and the involvement of various proteins and enzymes, ultimately leading to pro-hypertrophic transcription factors and cardiac hypertrophy. This slide shows the outcome of prolonged catecholamine stimulation, left ventricular hypertrophy, LVH, which can lead to cardiomyopathy. This highlights the importance of managing chronic stress and its impact on cardiovascular health. Catecholamines also affect smooth muscle contraction in various organs. They cause contraction of the splenic capsule, sphincters of the gastrointestinal tract, gallbladder, uterus, and the dilator pupillae of the iris. Stress hormones, released from the adrenal gland and sympathetic nervous system, can influence cancer development and progression. The adrenal gland is regulated by ACTH from the pituitary gland in response to stress. These hormones can contribute to angiogenesis, tumor growth, and metastasis. Adrenaline has several other functions. It decreases blood coagulation time, increases RBC count by releasing them from the spleen, and enhances the rate and force of respiration, causing bronchodilation. It also increases brain activity, enhancing cortical arousal, which leads to increased wakefulness, vigilance, muscle tone, heart rate, and alertness. Slide 26. Slide 27. Slide 28. Slide 29. Slide 30. Slide 31.